Another thing that we can do, check this out. If you click on that and you see the surface versus the orbit, when I get that to say orbit, it says that I'm going 175 meters per second. But Das, you're not moving. You're like sitting still right now, right? Actually, if you zoom out far enough, you look at the planet and you know that the planet, right, rotates like this. My pen! I need to find that pen cup thing, so I always put the pen in the same place. Right now, the planet is rotating, right? Kerbal rotates on its axis. This is the North Pole. And Kerbal actually rotates like this, right? Why am I going 175 meters per second, even though I'm standing still on the surface of the planet? The launch facility may be right here. This is the rocket, right? It may be sitting there, but because of the rotation of the planet, the rocket is actually moving 175 meters per second. Faster than that if you count the motion of the planet around the sun, da-da-da-da-da. But anyways, relative to the like center of the planet, the rocket is moving 175 meters per second. We can use that. We want to launch that rocket in such a way that we take that rotational energy, the velocity that we have because the planet's rotating and we're riding the planet right now. What we can do here, we can aim the rocket in such a way that we get to take that into account. So which way would we want to aim, right? Kerbal is going this way. And if we want to take off to take that into account, we want to make sure that we launch along the rotation of Kerbal's orbit. Sorry, Kerbal's rotation. If we look at this from the top down, and we kind of move this around like that, right? And we look at our launch facility. Where is it at? Here's our launch facility right here. And we have, let's do this again. I'm going to draw a globe. Oh, wrong button. I hit the wrong button. My bad. Say this is a globe, and here's the North Pole, right? And here's the South Pole sticking down the bottom. And we know that Kerbal is rotating like this. We want to match that rotation. It's not rotating like this, and it's not rotating like this. It's rotating like that right there on that axis from north to south. So if our launch facility is right here, we want to match that rotation. Do we want to take off and go north to the North Pole? No, we don't want to take off and go north. That would take us up towards one of the axes. Do we want to take off and go south to the South Pole? No, we don't want to do that either. What we want to do, knowing that the planet down here on its equator, is rotating like this, we want to take off in that same direction. And when we launch, we want to take that rocket off and go to the east, because that allows us to add that 175 meters per second of velocity that we get because the planet's rotating right now, and we get to add that to our orbital trajectory so that we can go faster. It's almost like free speed, right? Why would you do that? And the trick is, the follow-up question, right? If we came over here and we got rid of all this, and instead we launched to the west, what's going to happen? We've got 175 meters per second of motion in this direction. Use your units. It's behind my head. We've got 175 meters per second in that direction. If we launch to the west instead, we're going to have to overcome that rotation before we get up into orbit. So every single time we launch, when we're starting off just to get into orbit, when we launch, we typically launch to the east. Because if we launch to the east, we get that free 175 meters per second of velocity that we get to add to our orbital velocity. If we're going west, if we launch to the west, we have to do not another 175, we have to counteract the 175 and do another 175 on top of that. That means all of a sudden it's 350 meters per second extra velocity that we've got to get from somewhere if we want to go into orbit that goes west instead of east, right? This costs us 350 meters per second. My handwriting is terrible. That's 350D. More to go west instead of east. So when we're first getting into our orbits, we want to go to the east, right? Like this. And I always do the analogy, right? I'm not going to... That's not a very orbital-looking velocity trajectory. I always do the analogy, right? You know, like the moving sidewalks, right? You're at the airport, you're at the mall, or whatever, you have a big mall, and you've got those little moving sidewalks, right, that are basically conveyor belts that are hidden under the ground, and you stand on the conveyor belt like this. This is me. I should probably have on a hat. Like that, and headphones. Alright, that's me, okay? And I'm at the airport, or I'm at the mall, or whatever, and I'm on one of those moving sidewalks, right? And that moving sidewalk is, like, moving me in this direction, and I'm being super lazy. Like, I'm just, like, standing still. I'm not walking like that, right? That's my legs are together, so anyways, I'm not walking. But I can get some velocity from the little moving sidewalk, the conveyor belt sort of thing. It's going to move me that way. So if I were super unsafe, kids, and I were to run along that moving... Hey, that was actually a pretty good running thing. If I ran along that moving sidewalk and I jumped at the end of it, boing, I would have my velocity, how fast I can run, and I would get to add to that the velocity of the moving sidewalk. So I could run faster and I could jump farther if I ran in the same direction as the sidewalk, right? Let me see if I can't add little arrows to this. Like that. Those little arrows showing that the moving sidewalk is going that way. If I run the other way, right? If the moving sidewalk instead was going this direction, and I'm not going to redraw me, I'm going to make the moving sidewalk go against me, and I tried to run against the moving sidewalk, don't do this, okay? I would run slower and I would jump less far, right? Than I could. So whenever we take off to the east, when we want to lean our rocket over towards the east and we want to see if we can't get some of that planet's rotational velocity we get because we're riding on the planet and it's rotating about the center, that's the same sort of thing as jumping off in the same direction as the moving sidewalk, the conveyor belt sort of thing. Like that. Yes, yes, good. Alright, that's why we do that, I think. Cheating at the Olympic long jump, you're exactly right. I'm a big old cheater. Yes, please, please don't jump off. Don't jump off. Let me see here. Let me see if there's any questions about that. And then we will keep on keeping on. I'm going to come over here. You can't try this at home because you don't have a moving sidewalk in your house. Look, don't try it on a skateboard. Don't ride on a car and jump off. Just don't do any of that, okay? Just understand the analogy.